and we'll be covering neural nets today. So here's where we left in the last session. So neural nets, so take a look at this picture. This is typically what you will see if you Google neural nets. So today we'll make sense out of this first, and then we'll implement this using TensorFlow. So a neural net has these circles. These are called neurons. So what they do is they get input from other neurons, and they will apply a function or a transformation to whatever they get, and they give it as an output. And each input is going to be coming from a different neuron, and each output is going to a different neuron. So what happens is these neurons, they are arranged in layers, and so each layer is given a specific transformation. For example, you could probably apply a function so that all if the sum of inputs is a negative number, then your output is 0, and if the sum of inputs is a positive number, then your output is 1. That could be one example for transformation, and we will look into a much more complex transformation once we go on to image processing and all that. So keeping transformations aside for now, let us look at this diagram. So there is an input layer, which is where your input is going to be fed, obviously. And from there, you're going to have the input, whatever you're getting, that is going to the next hidden layer. All layers in a neural network that are not input and output, we call them hidden layers. So when these arrows take the output from the input layer, each arrow will have a weight assigned to it, weight as in a coefficient. So what happens is, from, say, we're taking the first neuron in the hidden layer. So from these 3 input layers, you are going to have 3 arrows coming in, and each arrow is going to have a weight, and it's going to multiply whatever the input layer has, and it's going to get summed up in this neuron, and then it's going to apply its transformation onto it, and the same thing is going to recursively happen for every layer. So that's essentially what a neural network diagram implies. So to get a more mathematical idea of what exactly is going on here, I have another picture in the next page. So if you look at this, so your inputs are x0, x1, x2. X0 is not xi here is not necessarily a number. It can be anything that follows addition and scaling. Basically a definition of a vector if you go in pure maths. What they'll tell you is a vector, unlike physics or the 3-dimensional vector you will be seeing, it's going to be an object that follows addition and can be scaled. And when you add 2 vectors, it should be another vector basically. And if you scale a vector, it should be another vector. So that's a definition of a vector. We're going with that definition. So x0 is a vector, x1 is a vector, and x2 is also a vector. And what happens is each arrow is taking its weights to the next, each arrow is taking the output in the previous layer multiplied by the weight that the arrow has to the next neuron. So in the first neuron, we have w0 x0 plus w1 x1 plus w2 x2 ... And the first layer is taking the sum of all of its inputs and applying a function on it, and that's what becomes the output of the first layer. So that is y0, y1, and y2, and so on. That's how this works. So by the end of 3 layers, you have this very complex function, which I have zoomed out because I couldn't even type it in space. So that's exactly what makes these neural networks very useful. Since this final output is so complex, the neural network is being able to perform complex tasks. And how exactly we use this setup? So we just saw how this information is passing on from layer to layer, but how exactly is this useful for us? So what happens is we will give this neural network a training set. So this is basically supervised learning. We'll give it a training set where you'll give the input and you'll give the expected output. And just like how we calculated error in linear regression, we're going to calculate error here. And there are different methods for it. And what we do is we minimize error. And when we minimize error, what we do here is we change the weights. So for example, if the error is going down, if I decrease W naught, then I'll decrease W naught, basically. So we'll keep on doing it until the neural network becomes more and more efficient in what we want it to do. So that's what the next slide is going to talk about in a more mathematical way. So learning from a training set. So what we do is we find the error, like I mentioned. There are many different types of errors. In this summer school, we'll be dealing with mean square error, which is the most basic one. We dealt with this in linear regression itself. And the other error is called categorical cross entropy, which we won't explain here, which you will use in one of your tasks. So yeah, say you calculate the error as a function of your weights arranged in a linear vector. So like that will be of this form. So w naught into its basis, its own basis. So like each basis is independent of each other. For example, what I mean by basis here is like I cap, j cap, k cap. So like if you have only three weights, you can just think of it like your familiar 3D vector. I cap, j cap, k cap, w1, w naught into I cap plus w1 into j cap plus w2 into k cap, like that. This is analogous to that. Basically, we have like a lot of dimensions. Don't try to visualize it. This is just for mathematically dealing with it. So we basically arrange all our weights in a vector, and then we take error as a function of this vector. Why we are doing this? This has no significance as such. This is just to condense notation. So because we don't have to write w1, w2, w e of w1, w2, w3 dot dot, we can just write this vector, and we'll see that we'll use the gradient. So like instead of writing derivative of e with respect to w1, derivative of e with respect to w2 dot dot dot, we'll just write the derivative. That's the only reason we are arranging it in a vector here. There's nothing else. So this is one way of calculating error. This is the familiar one. Say your task is a classification task, or whatever. So let's deal with classification here for now. So you have p0, p1, p2 dot dot dot. So that's the probability with which you predict something. Let me go back to the diagram here. So in this one, your p0 will be your output at the first output neuron, and p1 will be the output at the second output neuron. So basically here our task would be to classify into two classes with three inputs basically. So if you want to calculate error here using the mean square error method, you will take what the probability should have been if you were 100% correct, which is 1 in one of the neurons and 0 in the other. And then you take the difference between what you predicted and that, and then you sum the square of it. That's what I've done here. So one of the neurons will be the right one, which corresponds to 1. So 1 minus that pi squared plus the rest of the ones should have been 0. So the sum would just be p k squared. So that's one example of calculating error. And how exactly we optimize it? Once the error is being calculated, you can find how exactly the error changes if you change the coefficients. How we do it, we take the gradient. Gradient is just a vector of derivatives. So we will, like, if we travel opposite to the gradient, W is going to decrease the most. So what we do is error is going to decrease the most. So what we do is we decrement the weights vector with the coefficient into our gradient. And this coefficient in this particular method is called learning rate. In a different method, learning rate could be something else. But you get the idea, right? Learning rate means how fast you are optimizing. So this method is called SGD, and GD here will be gradient descent. If you get why it's named like that, we're using the gradient and we are going against the gradient. So that's how learning works. And if you have any doubts still here, you may ask right now. I'm assuming there are no doubts. I'll quickly go back to the start and run through it once more because this is important. So this picture is how a neural network works. Each neuron has input and output, and each neuron will do some kind of transformation to your input. Input layer doesn't. Input layer is just a dummy layer that does nothing but just gives you the input, like x0, x1, x2. And when you have, and each arrow here is taking the output of one neuron into the input of the other into a weight that is assigned to that arrow. And each neuron takes all the inputs and sums them and applies a transformation. And the output layer is what you get out of your model. So this is what it mathematically looks like. And what we do here is we optimize these weights so that we get the neural network do its job. So we calculate error and then we optimize it using something with the error. That's a quick recap. And here are some details we might need later. So the transformation that I mentioned for so what we are first dealing with are called artificial neural networks. These have only these kind of linear layers, if you get what I mean. Just there's just the sum of it, and then there's a transformation which is just a function of it, and it's not very complicated. These layers are, these neural networks are called artificial neural networks, or ANN. And by the end of this course, we'll deal with CNN. So that's why I'm making the distinction here, right here. So in ANNs, the transformation we apply is called the activation function of that layer. So the entire layer will have the same function, and that function is called the activation function of that layer. And I've listed 4 activation functions here. You may refer to this whenever you are working with your implementation. And the error function we used is called mean squared error. We talked about that. The optimization method we used is called SGD. We also talked about that. And one thing I didn't show in this diagram is that in each layer, the input also has a bias. That is a constant term plus C. So here I have shown f naught of omega naught x naught plus dot dot dot. But in the end, there will also be a plus C naught. Because when you just take inputs, sometimes you might not get the most optimal net. So we also have a constant term. And there are, and in this, while we deal with neural networks here, we won't talk much about overfitting or underfitting. So that we'll deal with that later, and we will not deal with that in much detail. So I have linked something here on the PDF, on the slides. You can read it up if you want later. So that is pretty much the theory behind artificial neural networks. So now we will see how exactly we implement these. I will give you an idea of how exactly it works, and then AM will show you a Google Collaboratory implementation of it. So first we import TensorFlow, and we just import everything we need. So our first step will be to vectorize our data. In the input layer, if you recall, we had defined a vector, and we said we need the data to be a vector like that. So what we do is we do something to the data so that it follows addition and can be scaled up and everything like that. For example, say if you have a point in the Cartesian plane, and then your neural network is supposed to classify it into being inside some curve and being outside some curve, or something like that, being inside the unit circle or outside the unit circle, something like that. So our vector here would be of 2 input neurons and X and Y. So basically whatever I've shown here. And say we are dealing with an image, a colored image. So how exactly this will be vectorized? So you can take the brightnesses of each color at each pixel and arrange it in a matrix, in a 2D matrix. And we know that matrices do follow addition and can be scaled up. So they are technically vectors too. We call them tensors in when we're talking in a computer science context. So yeah, that's how you vectorize an image. And in this case, you will have 3 input neurons because you have red, green, and blue. So 3 input neurons, each of uh, 2D matrices, and the matrix elements will be the brightnesses of the pixels. That's how we vectorize image data. So our first step is done, which is vectorizing data. And then we'll go on to building this model in TensorFlow. We will be using this API called Keras. So what we will be doing is for ANN, we'll just use a sequential model. Sequential model is whatever I showed here. Everything is connected to everything else in the next layer, and it moves on as a sequence. There's no connections cross layers. There's no connection between the input layer to the hidden layer 2 directly, or the hidden layer 1 to output, or there's no interconnections like that. So it's sequential, and every previous neuron is connected to every other next layer neuron. So that's a sequential model, and we will be using only dense layers. So okay, I was here. Yeah. And we won't, yeah, like I said before, we won't discuss choosing the size yet. We will come back to that. And even when we come back to that, we won't be discussing it in much depth because we're not approaching it in a theoretical way. We want to implement this in our project, in our case study, basically. So here we go. So this will create a neural network object, and it's given a list of layer objects, which might look like this, which might look like a list of this function, several this function I've mentioned here several times. Like what I mean is a list of dense of something, comma dense of something, comma dense of something, comma dense of something. That's what a list of layer objects look like. And so what exactly is dense of this? This is one of those hidden layers or output layer. So if we are replicating whatever picture I showed you guys, we'll have 3 layers. And we will, so the point to note here is we won't exactly use dense of for the input layer. What we do is we just give the shape of input in one of those dense layers, in the first dense layer, so that the number of input neurons is implied here. And we have the activation function, 4 of them which I listed before. And this name is optional. You don't actually need to name your layers. And A here will be the number of neurons in this layer. So for example, so let's say we are to build this neural network that I showed. So what we will do here, so what we will do is our list will contain firstly a dense layer with 4 neurons, and we will mention the input shape there to be 3 comma. And then we'll have another dense layer with 5 neurons. There we won't exactly mention the input shape because it will just receive it from the previous layer. We mention the input shape only in the first training layer. And then we'll have the final output layer, which will be dense if 2, and an activation function, of course. So that's what your list of layer objects will look like. And after creating a neural network object, we will compile it. When we compile it, we'll give it what error function we want it to use. Error is called loss here. What loss function we want it to use, and then we'll mention the optimizer we wanted to use. So the optimizer example we saw was SGD, but it's a better practice to use Adam. Adam is one of the best optimizers. So we'll stick to Adam. And in case you don't want the default learning rate, you can, we'll come back to syntaxes in the collaboratory, but you can use a syntax of this sort and change your learning rate. So this is the default value. You can make it smaller if you want. We'll see when exactly we make it smaller. And metrics is what each time you train the model, whatever you ask it to print it, it's these metrics. So like if I want it to print the accuracy every time, so I tell it metrics equals list of accuracy. So that is how you build a model. So we vectorize data, we built the model, now we'll train the model. So to train it, we have model.fit of. X will be your vectorized data, and or like let me take an example here. So we dealt with image data. Okay, no, not image data. Let's take XY itself. So X will be an array of your vectorized data. What I mean by that is X. Let's say we have 1,000 data points. Then the shape of X will be 1,000, 2, because we have two variables X and Y. So what exactly is X? It is an array of subarrays of the input shape, the input shape that we mentioned here. So it'll be an array which has subarrays of this shape. It is an array which has subarrays, which is the vectorized data basically. And y is just the same thing but for output. It is an array of subarrays of the output shape. And epochs here is the number of times you go through the entire data set. For example, say I have 1,000 data entries, and when I train it once, it is going to have an influence of the last element more than the first, for example. Or maybe it did not really, it had more influence from the first element than the last, or something like that. So to avoid that, we will run it again through the dataset. And not only that, since it's starting from nothing, from just randomized weights, and it's building up to an optimal neural network, it'll not exactly reach its optimal state in one iteration of the data. So we'll iterate the data several times, and this is what epochs means. So if I give it epochs equals 150, it will go through the data 150 times. And batch size, so we'll take the SGD optimization method again. So I say the batch size is 10. Then what exactly happens is it'll calculate the gradient for 10 data entries, and then only update your weights vector. This is done so that it doesn't keep updating on each data entry, which will sometimes not make sense. For example, say one of your data says go right and the other says go left. So you'll keep going right, left, and you'll not end up anywhere. So the same thing if you take it in a batch. So you might end up at somewhere in between where it's like the sweet spot. So that's why we take data in batches and then train them on. So yeah, so once we run this function, what it does is it takes all the x values, feeds it into the input, and then sees what y values it gets and compares it with the y we give it, find the loss function, and then optimize the loss function, and then do it over and over. And x is given in batches, and it updates the weights vector only in batches, and it does it over and over until 150 epochs is reached. So I'll repeat what I said. So what happens is x is given to the input layer, and you get some y, and y is compared with the y we are supposed to get. And this is done in batches, and at the end of each batch, the weights vector is updated. And the entire data set is done in batches like this for 150 iterations of the entire data. That's exactly what this does. And once we train it, we test it. So there are two things you could do. One, you could evaluate if your model is actually good, which is model.evaluate. This is usually done with the testing set. So what we usually do is we, just like how we did it in linear regression, we'll take the data we have, we split it in two. We'll train our model with one part. It won't be half. It'll be like 80% of the data. And the other 20% we'll use to test if the model is actually working well. Only then we'll deploy the model. And predict off is used when you've actually deployed the model. So say the model is out, you are done with training it, and then you put it into use. So when you do that, you give it, just like x and y, you give it an array of subarrays of your vectorized data, and then it'll give you an array of subarrays of the output. And since we originally did not deal with underfitting and overfitting, we'll do it here. What happens is once you've done model.evaluate off, you might realize that your model is underperforming, and it's probably having very good accuracy in your testing set, but is not doing well in your training. I mean, very good in your training set and not doing in your testing set, or probably it's not doing well in both, or it's just probably running for too long, or it's just probably saturating at some point and it's not improving when you improve the box. So this step, it involves a lot of experimenting. You'll have to see what increasing the size does, what increasing the number of layers does, what increasing the learning rate does, what increasing the batch size does, and everything. We have a small list of observations, and we'll tell you this might not work everywhere. So if you see that the accuracy saturates, you're probably not using the right optimizer. I would just say switch to Atom and not SGD. And if your model is not even working, like it's not moving anywhere at all, then you're probably using the wrong loss function. For example, if I use the other loss function I mentioned, categorical cross entropy, in a task where I have only one output neuron and that is a value that I have to predict and not exactly a classification, then it won't do anything because it is a classification task loss function. And it's not something like mean square error. So it won't work. So in that case, I will have to switch back to mean square error. And the same thing, if I'm using mean squared error in a classification task, it will work well. But maybe switching to this categorical cross entropy will give me better results. And if the accuracy saturates at some point, then your learning rate might be too high. How exactly this works is, say some of your data says go to left, or okay, not left, right. Let's say up and down. Up and down your value that you predict. Say some of your data says go down, and your learning rate is too high, and you go down, but you go too much, and the rest of your data says doesn't say anything. So what will happen here is you will go down more than how much you should have. So there's no coming back. So in this case, your accuracy will saturate to how much ever you've gone down, basically. So these are things to do with learning rate, optimizer, and loss function. Now we'll move on to the size. So let's say your model performs very well in your training set, as in you're getting 95%, 98%, or whatever. But then when you do evaluate off and you actually test your model, it only gives you 50% or something. Then this is a case of overfitting. We will not go much into the details, but I'll tell you what to do here. You will either have to decrease your layer size or decrease your depth. And what to do here, you have to experiment. If you want your data, if you want your model to do complex tasks but not overfit, you'll probably decrease your layer size. If you want your model to, if it's not really that complex of a task, but it's still overfitting and your layer size is already small, then you decrease your depth. Depth here means the number of layers. So the opposite for underfitting. Underfitting is when your accuracy is bad in both training and testing. Think of it this way. Let's say you're trying to fit a straight line like we did in linear regression to a data that is actually a parabola. What will happen here is no matter how much you try, error is not going to go down more than some point. This is exactly what underfitting will look. So what you do here is you increase the size of your layer somehow. If you wanted to do more complex tasks, like say classifying images, you will increase the depth. Meanwhile, if it's not exactly a complex task, but you just want it to be larger, you can increase your layer size. So yeah, that is about tuning the model. So now, if you have any doubts so far, you can ask now. After this, AM will go on to implementing an ANN for you guys.
I'll give 2 minutes break, like for doubts and all. Then after we'll go to
Yeah.
implement.
Hmm. Oh yeah, this is something we have to mention. Sometimes your data set might not just support that much accuracy. In that case, well, you can't optimize beyond some point. But so yeah, whatever you try to do, you try to maximize it. Uh, but just because we told you this, you can't like not try to optimize it more. But what I mean to say is, in case you do have a chance to increase your data set's size, that is always favorable. And since we have time, I think I'll just show you what overfitting might look like. So let me just see. So let's say our neural network is supposed to do this task of splitting the. Okay, let's just take a square of side length 1 each. So let's say this is just the first square in the first quadrant from 0 to 1, 0 to 1 in x and y. And our task for the neural network is to, given a point, tell if this point lies within a curve or not. So in traditional programming, this is a very simple task. You can just put if and then one inequality and then give the answer. But for machine learning, I wouldn't say it's not simple, but we'll implement it just like any other machine learning program. So your input, like I said, will be x and y, two input neurons. So the input state will be 2 comma. And your hidden layers and all that, you somehow figure out how many exactly you have to place. And then your output will be one output neuron, which goes from 0 to 1 because it's a binary data. And one means it's within your curve, and 0 means it's outside. So with that in mind, with this model in mind, we'll discuss overfitting and underfitting. Let's say your model is underfitting. So what happens is, whatever point you give it, it's probably going to tell you something that is never as close to the correct value. Uh, what I mean by that is, uh, let's okay, let me see if this link has pictures. Hmm. Give me a second. Okay, so this is the first picture that comes up when you search uh, overfitting and underfitting. Wait, let me get a better picture. second picture. Okay, so this is the exact same task I just told you guys. So what is happening in underfitting is the data is not the line in which with which you the curve with which you divide your square is not exactly complex enough to actually represent your data. So here you needed a parabola like the appropriate fitting they've shown, but then you try to fit it with a straight line, then you're going to get a lot of error because these green areas are going to be there, these green areas are going to be there, and these are going to come to the other side. So that is underfitting. And overfitting is when you just run it too much into your model that your model is perfect for this data that you've given it, but then if you ask it to perform some other task, it's going to not perform just as well. So in this picture, so there is something on this data set and there is a green point here, and but then you don't want it to whenever you give a point there, you don't want the program to predict that it's a green point. You want it to predict that it's a yellow point. So this is when overfitting is bad. And in this point example, I just took this to make it clear. In a real example, say you're classifying digits. What will happen is if overfitting is just fitting your data perfectly, and you give it some test data in which the digits are written a little differently, it might end up predicting wrong. That is where overfitting will become a problem. So this is why I told you guys, in the training set it might perform very well, but in the testing set it might not. And underfitting will perform bad in both. So yeah, this much we'll talk about underfitting and overfitting. And where exactly this will be useful is when you do your tasks, you might realize that something is wrong with your model, but you can't figure out what. And there's just too much to experiment with. In that case, if you manage to realize that it is underfitting, for example, when you try to print what it predicts, and it always prints something close to 0.5 or something, but then you expect it to be 0.9 or 0.1 or something like that, like, you know, closer to 1 or closer to 0, but it always predicts 0.5, then that is definitely underfitting. And what exactly is happening is it is just picking one value at the center so that it is minimizing the error as much it can, and how much it can is very small. That is an underfitting. And overfitting is going to be very clear actually. If you look at your program running, your training set will reach 90 very fast, but when you actually try to predict, it will be very off. So yeah, from here AM will take over.
Yeah, just give me a minute.
Yeah, cool. I'll cut screen share.
The screen is visible, right?
Yeah, visible.
I'll go to. So as I just explained in the theory, single layer precipitation is like that. It give you add input and it has weights ready. So it just like a linear equation, it adds the weight to the input and then sum up, and there is an activation function which activates like this kind of activation function which gives final output, right? So you give like x1, x2, x3 any values, then there are the, while training it will like to fit the model best, it will find out the weights during training and apply that weight to the like final result, right? So when you apply the weight, it sums up all the weight into input, and after summing up, it applies the activation function, which gives the final output in precipitant. So the commonly used activation function are here like sigmoid, ReLU, TANH, maxout, and like we'll be mostly using ReLU, sigmoid, and soft. And there's one more is called softmax. You can like research about that. That's also like sigmoid and softmax are like used for uh, like classifying the final one. ReLU is mainly used for see when you apply sigmoid function, it will give a value of 0 to 1. But in ReLU, you see that the final value will be like, if it's positive, it will give that value only. But in case of a sigmoid, it will only give value from 0 to 1. And max out is maximum between two values, like two weights, basically that. So we'll go down how to build a layer. So as you can see, like in a neural network, like you give input number of inputs nodes and give one output node. Here is specified here. Then as he explained, model dot sequential model. But I'll go till there. Yeah, sequential and dense. You can see that. Hey, as he explained, model equal to sequential into a list of layers. So we can also write this as model. I can see you how to write this code in two ways. You can either write dense like this. I can remove this. Either write this or like this. Both works. These are the two ways of writing, like sequential and adding layers to this. And these two are equivalent. Like you can use whatever you are convenient with. Here we're just adding a like what dense layer, which is this, using output nodes, two output, like one output node and two inputs node, and defining one hidden layer which has sigmoid as activation function. Basically, that. So build basically one layer, one hidden layer, single precipitant node. First neural network will be. So from next we'll build multi-layer precipitation, which is like each node is connected to like there are two layers. Every node is connected to other node. Like every part of one layer is connected to every part of other layer. As you can call it as a fully connected layer. That's basically. So this is how an MLP basically looks like. It's there in the slide also. Basically this. It takes its output and goes with activation function and then gives the final output. You can define your initial input layer and output layer and You can define any number of hidden layers in between and the size of the hidden layers. Now we'll generate some random data and build a neural layer and see how it works. So basically we train data from NumPy library using random. We did some random training data and random testing data and labels. After generating it, we'll build the model. So here we define units as the units of hidden layer. So like there will be 32 nodes in the one hidden layer. So as you can see, we use the modern sequential. Then we did model.add as, or you can either write inside sequential as I will say. You can just write this also. Any as work, but this look more structured, so I prefer this. You can prefer anything you want. And here input dimension is 100. In the first layer you have to specify the input dimension. From then it will take care of it. And in the last layer the number of units is the final output layer basically. And here we have used two sigmoid, two hidden layers using railway activation. After that we have used uh, like output layer which is specified as 1 because it gives one output. That means we specified 1, and activation is sigmoid. As I have written, the output should be a single outcome, so the dense layer is defined with a single one. And similarly, as explained in the slide, the loss functions, optimizer, and matrices. And loss functions are used to like as you train the data, same as mean square error and categorical cross entropy as explained in the. And matrices are basically accuracy, precision. These are matrices. You can call them. And optimizers examples are gradient descent or Adams. Adams is usually more powerful. So by like use Adams and categorical cross entropy mostly in this notebook. But still, I will show you with gradient descent. We have see in this code I'll say you how to import optimization and losses. So basically using TensorFlow that Keras it optimizes, you can import every. These are the optimizers you can like see. If you want to learn more about this, there's a documentation link in the notebook. But I'll send this notebook chat in the link. You can also run along with me. The LR is basically the learning rate, whatever I mentioned in the slide. And these are, and you don't need to look into this. Just ignore this. I think like these are there in the documentation. You can just keep it as default. Like you can just erase this and the default value will come. Just keep as learning rate. And these are the losses, different type of losses like categorical cross entropy, mean squared error, mean absolute errors, and matrices are accuracy, precision, and recall. So I'll go down. Till now, anyone has any doubts? I have no doubt. So the first data we generated, we'll test our model on that. This model, it's obviously not a like great model, but we'll see how it. Just for example, we'll test the model on the random data, and the data set is random, so uh, it doesn't have any pattern. So you can say it will give obviously less accuracy. You can see when you run the code. Let me run all. See, The accuracy is coming out to be test is 0.460 means 46% and training accuracy is 51%. That means the dataset and model both are like not so good. A dataset is obviously not good since we randomly generated data and it doesn't have a pattern and it cannot recognize. And the model also, it has only 2 hidden layers. So like this is how you build a neural network and implementing it on random data. Now we'll go to managing overfitting and all. Till now anyone has any doubt, just ask me. Okay. So how to manage overfitting? Okay. So like wait, this is the loss or error, and this is number of iteration or equals. What does the ideal model look like? The if this is the training set, the validation set will be close to this. Like it will go like this. It won't go. If this goes up like separated on each iteration, then you can say that the model is overfitting. Like if you see here, the training accuracy, like training loss and validation loss after like so an example. Here is the loss and validation loss. Okay. When like training loss and validation loss are close by, then the model is working fine. Like if the difference between training loss and validation loss is like they got separated, like on increasing the number of epoch, the difference between training loss and validation loss is increasing. That means the model is overfitting and it cannot work on new data. So it gets too overweighted to training data, so that when you get like give a new data to the model to predict, it fails to do that. So in graphical way, just this plot the two lines, validation set and training set, need to be close together. If it's going away, then like, the model is overfitting. So to manage overfitting, what we can just do that in the units of the hidden layers, we can just disable some layers during training. And that's what dropouts do. The dropout on a hidden layer, it randomly puts some number of percentage. You give the dropout, say the dropout is 0.2 to 0.5, mean 20% to 50%. So whatever percentage you give, that number of units of a hidden layer, it disables that amount of file training. So the overfitting reduces and like the model perfectly. And next we'll go to your list hopping. So there is an option to monitor the validation loss while training. Like you can, there's a library in TensorFlow callback or model checkpoint. You can like using that model, you can just monitor the validation loss, and whenever on increasing the number of epochs, the validation loss, if the loss increases, then what the callback calls is like it stops the training there and goes into predicting like the if you give your number of epochs as 100, let's assume that at 67th epoch the validation loss didn't improve and it went down. So what this callback does and the early stopping does is they stop this training at that moment and goes on to predict new data. So another one is checkpoint. Uh, in model checkpoint, what does model checkpoint does? Hello, am I audible now?
Yes.
Yeah. So what does a model checkpoint does that it goes through all 100 epochs, but when in whatever weight the validation loss and validation accuracy are best, both training and validation, and they're close by, so no overfit. At that point, it saves that specific weight, and like it saves in a file and uses that file to predict the new data. That's what checkpoint and the list of are. So anyone got any doubt in this? Now I'll go to applying neural network in MNIST dataset and just give 1-2 minute break and then we'll start. We imported all our, so I'll start. So MNIST is a collection of handy-10 digits ranging from 0 to 9. So like it has 6,000 images and 1,000 test images. They're classified into corresponding labels and categories. So to use MNIST dataset in notebook, Keras is provided to download and extract images and label. We can do that. So we'll show here that how to train the MNIST dataset and find the accuracy basically. So we'll import all the libraries first. Then you importing the dataset using this command from Keras datasets. You can import the MNIST. And to load the dataset, you can just use MNIST.load data, and this command is like splits the dataset into string whitelist and xtest and whitelist. Now we'll encode the data. So how are you gonna? I'll define an encoder. So we'll prepare a list L, which is from 0 to 9, and for like in that list we'll look through. I'll show you right. What does Renstein gives? It gives us an array of 0 to 9, or list you can say, a list of 0 to 9. So we'll select each I from 0 to 9, and from that, like L is basically list like 0 for every I in like 0 to 9, and L of X is like X is basically the indices of the list L, and it will give the value 1, and we'll just return the value L in this function. Do you understand anything? Not quit. I'll show you what this the function returns. New code. This is how it prints. If you say encode digit 2, I'll keep a range to it. Print. Just see this matrix. This is what the function does. Like if you put I as 0, it will give 1 at that point and 0 at rest of the point. And if you put I as a number, let's assume 4, it will give 1 at the fourth indices of the list and 0 at the all of the rest indices. So this is how it works. Now we'll resize and normalize the dataset. Using the extended reshape, you have extend in any shape, like in given whatever default shape in the dataset. We'll reshape that to number of classes and 28 plus 28 images we are using and 1 are leaving. And same as 28 plus 28 into, okay, I'll train the shape for you, print the shape for you. Next. So this is what there are 6,000 training images. All have, like, as you can see here, it's written here. There are 60,000 training images and 10,000 testing images. So 60,000 images, all of them 28, 28, 1 safe, and similar to X test 12. There are 10,000 images, each we got 28 plus 28 into 1. And we rescale the images by dividing by 225. And we change the type to float 32 for our purpose. Now what is this does, like you say, it encodes the like digits in Whitelane to like what 0 to 1, like that you can say. If there is any number, like it goes through the list of Whitelane, like I'll print the Whitelane here. So yeah, so initially the wait okay, since we updated the variable, now I have to load the dataset again, I think, to show you the example. Right, I'll show you how it's done. 1 minute, give me just a minute. String1, I'll create 4 more variables to show you the difference between these two, and also you see these are the array 5 4 5, like this. What this does, this white line, like this encoder here, it's 5. So what is the for this list at indices 5, it gives 1, rest of the indices it prints 0. Same it does for 0, at index 0, index 0 it prints 1 and rest of it gives 0. Like that for all the elements in the array, it creates a 1 0 list like that. Now if I like got the action item, now I'll create our model. Model, let's see, you can use either this or this. As I said, either this or this, anything works. I am using this because this is like looks more easier to debug it, not so messy, and it's structured more. We flatten the layer uh, to give input into the dense layer. We don't need to flatten also, it will be either flattening, it will also be fine. Now we created our first layer. The input shape is 28, 28, 1, and activation is ReLU, and the number of layers is 256. And after that we added a dropout of 0.4, and then we created one more layer, dense layer of 256 hidden units, and using activation ReLU. Then after that we added dropout of 0.4. As you can see, it like cancel it crosses out 40% of the layer so that the data doesn't overfit. In the final layer, since we have 0 to 9, 10 digits, so it should give 10 outputs. So final output layer is of 10 units, and we used activation softmax. This is the model, and the matrices we used as loss function as categorical cross entropy, optimizes RDM, and to evaluate we used accuracy. I'll show you the difference between this is how the accuracy Adams printed. We got test accuracy as 98% one. Now I'll show you how different does SGD and mean square error gives. Now we'll use this model. I think I haven't printed right. I'll just clear up this. Give me just 1 minute. Just read them. I didn't from start. I think something. So we're just this is what the training group like model that fit. This is how we train the data, and we are training data set with X train and Y train, and if number of epoch is 10, and we kept batch size as 128, and you can either use this or you can skip this also. This verbose address is verbose shell. If you keep it as 0, it doesn't print validation loss and validation accuracy at each step. If you keep it at 1, you have to give the validation data, and it will print validation loss and validation accuracy at every step. Here you can see that validation accuracy is 5.54%, and this is because we use standard gradation like SGD and mean square error. If we use RADAM, it will give better. So first I will show you how to do without this. You can just remove this and print also. See, it will just give loss and accuracy just for training data. It won't give validation loss and validation accuracy. But if you include this validation data and verbose equal to 1, it will print validation loss and validation accuracy at each step. Now I'll show you using Adams and cross entropy. Using the three dots, we just comment the code, like the code won't run, right? Basically like comment. Now we compiled with categorical cross entropy and Adams optimizer. Now we'll run this. We kept verbose as 1 to give value accuracy at each step, validation accuracy. You see the first accuracy itself is 0.9568, and it's increasing at each step. And using this, we just went the final test accuracy, which is 98.1%. Now, using this, we'll plot accuracy and loss plot for each epoch. Like in x-axis, we'll keep the number of epochs, and the y-axis is first plot is for accuracy, graph 1, and second graph is for cross entropy loss. As you can see that when starting the accuracy are like far away, but as we increase the number of epochs, training accuracy and validation accuracy are like getting closer, so it's fitting nicely. Same for loss, you can say, as it goes like near the 10th epoch, the data is like is merging. We'll increase the number of epochs and we'll see what happens. I'm keeping it 20. Let's say 30. 25 is fine. If it's overfits or not, we'll see. And see your validation accuracy is decreasing. Then it's increased. You see the final accuracy is 98.4%, I think. But let it run first. Yeah, you can see the as you increase the number of efforts, the accuracy improved. I'll plot, put in loss and accuracy. This is see the training loss is here 991. The separation between both the losses are increasing. It means the data is overfitting. You can say as we increase the number of books, the separation is increasing. That means the data is overfitting. So I can increase the dropout percentage or decrease the number of epochs so it doesn't overfit. And I'll keep it at 10 inputs only. 10. After that, it's overfitting. So, what if it's operating? What will we do? Like, basically, you just keep a callback like list model checkpoint, and I'll show you how to add model checkpoint. Just give me a minute. I'll just stopping sharing for a while. I'll come till model. Give me just a minute. Is visible? The screen is visible, right? So in the model, we can just add a checkpoint. So for as the checkpoint will store, I'll add the model checkpoint. Okay. Fine. I'll import here only. So yes. Yeah. We need to add a file for like the model will store. What this model checkpoint does, it stores the best words into a file and use that to predict basically. So for that we need a file path. So we'll just give, let's say, best model best weight dot file checkpoint equal to no. Say file path. Then I'll give the monitor attribute. You can see that this is what it gives automatically, so I'll just use it. Monitor while accuracy. Monitor the value accuracy, and I can say if you have to save best only as true. Modus max. And you can say callback. That's fine. I'll just, and we'll see the model that fit that attribute. Yeah. Callback as callbacks. I'll give this as callback checkpoint. Now I'll run this. Oh, we haven't run this. We'll keep epochs as 25, 20 only. I'll just compile. Oh, 1 minute. A minute to fix it. Yeah. Should work. Just use this as a. You can see there is a file created waste weight at 5, and to predict data you can just use this. See, it's training. Let it train first. So I'll just model best model as just define best model. Is waste weight. Now I'll evaluate this more with the training. Now I'll use this. Just give me just a moment. Just syntax of this. So here its accuracy is 98.1%. You can see from here. And we'll plot first, and we'll see where the best weight is. So here there's no overfitting, and like you can see the like the graphs are properly close by. So our best model is stored in this file, and I can load this and use it to predict data. So loading and using the model, I think, will using the next class while predicting the values of we'll use the model to predict the classify which garbage it is in the further session. For now, I think just using callbacks is fine. If you have any doubt on using callbacks, then you can just ask. Just add a file and the model checkpoint. You can go through the syntax in the documentation in the official TensorFlow site. There you can get info. There are monitoring value accuracy and the best accuracy keeping. So it will just keep the best accuracy out of this value and print here and save in this model, and we can load this model and use it to predict the data. We'll do that in the next session while predicting the same images, classifying as the automatic waste segregator does. It takes any image of the trash and classifies into categories. So using like this, we'll try to classify. We'll do in the next session. I think this much is enough for this session. If anyone has any doubts, you can speak up. I have shared the link of this notebook. You can just use. Rishi, is there anything else?
If there are no doubts, then I'll give off tasks right now.
Yeah. Okay, I'll stop sharing.
Okay, cool. Let me open it first of all. Okay, cool. So yeah, like we said, all three tasks we'll give you one deadline, not three deadlines per task, one deadline per task. So for the second set of tasks, we want you to generate your own data set using NumPy, random, pandas, whatever. What we want you to do is take the unit square in the first quadrant, and your label should be 1 if it's within the curve r equals sine 2 theta. Let me just quickly plot the curve so that you know what it looks like. R less than sine 2 theta. Okay, so what we want you to do is, and what happened? Okay. Okay, cool. So here's the unit square. We want you to generate a data set as a CSV file in which you have X, Y, and label. And label is 1 when the point lies in this area, and 0 when it lies outside. And with this data set, what we want you to do is, we want you to build an ANN and predict, given X comma Y, predict if it lies within or outside. That is, predict the label. So for example, if your neural net predicts 0.9, that means you are 90% sure it's inside and 10% probably outside. That's how we want you to give the output. And we, unlike the first set of tasks, this time we want you to submit. So basically, we want you to copy what your output is. So the output is probably going to look like whatever AM showed you. I'll show you in the next slide also what it will look like. So we want you to not screenshot, but copy the text and show us the output you're getting. So that we look at the accuracy you're getting, we look at if you are overfitting and stuff like that. So this is roughly what it might look like. So if you see, it's starting from some point and it's steadily increasing to 0.88. and your test data is somewhat close to 0.88, meaning it is not overfitting. We want you to submit something like this, not a screenshot, but like text. So we'll look at it. That's for problem 1. And for problem 2, we want you to build a multi-layer perception thing, which is just the neural network, which takes 2 inputs, which are binary in nature, and gives XOR output. XOR is basically this, if you have not seen before. XOR is if both your inputs are the same, then your output will be 0. And if both your inputs are different, then your output will be 1. So we want you to build a neural network that will learn from like you will have to use these 4 as your data set. There's nothing else. So we want the neural network to learn from this, and then if you give it A and B, it should give you the XOR output or something close to like 0.99 or something. So those are the 2 tasks. For the second task, we want you to give it all 4 possible inputs and predict the output. So basically, if you give it this left side of the table, we want the output to be the right side of the table. So we want you to submit again, copy the text and submit the output. So like, for example, the first entry is probably going to be 0.1, second going to be 0.9, something like that. We want you to submit that. So yeah, that's tasks for this session. And we have our customary memes for this session as well. Thank you for attending, and we'll see you in the next class. Bye-bye.
Thank you.